Mountain glaciers are one example where the signal we're seeing is really strong, and the question is really, is it related to anthropogenic global warming, or is it due to something else? We'll see that that something else is the exit from the little ice age, and we'll talk about what that means. Let's start with some classic pictures. This one is a glacier in Alaska, and you can see the retreat over only 6 years. Look how dramatic this is, a picture taken exactly from the same angle. On the right, 2015, on the left, 2009. This one is from Switzerland, and the glacier retreated by 500 meters, and you can see the big difference right here between this and this, and the slightly bigger melt pond at the end, melt lake at the end. This one is impressive. So this is in Peru, and it retreated by 1 kilometer, but you could see how dramatic is not just the length, but the volume, because this is a deep valley and it was completely covered by ice before, right? And finally, this one in Switzerland again, retreated by 1 kilometer over these 9 years. So again, a dramatic change over a very short period. So I mean, the change really is very dramatic. Okay, let's look just at a couple of videos.
A recent expedition up Mount Baker in Washington state reveals a stark...
Why do we care about mountain glaciers melting, by the way, apart from the fact that it's too bad they're lost? For practical reasons, does it matter? There are many places, in many places of the world where agriculture and other users of water rely on the storage during winter of snow and the release during spring. If the mountain glaciers don't exist, that storage disappears.
This is the story.
Okay, one last one about another reason that we might care about mountain glaciers melting.
Imagine a whole lake rushing down a mountain at once.
So you're about to plot glacier records, so let me just explain one small thing. So if you have a mountain and there's a glacier here, it will typically be going downhill, and then you can measure the location of the edge. Or if you want, you could measure the length of the glacier. Say, this is the length. And the issue is the length of the record as function of time over the last 100, 200, 300 years. So what you're going to do next is plot this record as function of time and see how glaciers have changed over the last 150 years or so. We could start with that. So that's going to be workshop 1, basically. Did you see this in your notebooks? Here's the fuller picture. So what do we see here? We see, first of all, the length time series. So this is in kilometers, right? So you could see 2 kilometers, 0, -2, of the length relative to the length at 1960. That's why they all cross 0 right here. And these are like 879 records, which is a lot, and clearly there's a downward trend. Okay, well, you could look at this in a different way. You could look at this map and plot a red sign where the glaciers are declining and a blue sign where they're increasing. And what I did here is plot the blue ones on top of the red ones. There are a few blue ones, you can see that here. But there's no question that the 29 glaciers with positive trends are completely dominated by the 791 that are showing decline. So there's no question that mountain glaciers are declining globally, right? And you're seeing this when you plot it yourself. So now the question is, why are they declining? That's our next phase, okay? So let's see, what are the possibilities? So you'll look at this later. These are the binned ones, so you average them all together, and I think it's interesting to look at the number of observations, right? So look at this. In the 1850s, there were just a few, but as you go forward in time, you have many observations. So this declining trend is very well documented. There's no question that there's a decline, and there's no question that the data are very extensive. Here's one estimate of the global temperature, global mean surface temperature anomaly. So you see that this is an anomaly because it's relative to something here. And you see us here, the increase, the recent increase, and you see the little ice age. So our hero today is the little ice age, okay? You see this period where the temperature were a fraction colder than what they were here. It's really a fraction of a degree. But that fraction of a degree did make a difference for temperatures, I'll show you in a second, and also for mountain glaciers. So let's look at that first. So this is Eric the Red, who explored Greenland. I think he was kicked out of, I forget where in Scandinavia, and he went and found Greenland. And of course, Greenland is a mountain of ice, but he went and told people that he found Greenland, which is a much more attractive sounding name. And then people immigrated to Greenland thanks to that, thanks to his sales abilities. And but then at some point, they had to abandon the colony because of the little ice age. So here's what it looks like. These are the remnants from 1408 of these settlements of the Vikings that then had to be abandoned because of the cold temperatures during the little ice age. Okay, you can see here, could not be maintained because of the increasingly harsh winters and so on. Okay, here's another evidence. So this is the Thames in England being frozen in 1677. It never happens today, obviously. So the little ice age caused this freezing of the river. Here's another one in Rotterdam. And yet another one in the Netherlands where you could see people ice skating and so on the frozen river where that or lake that isn't possible today. Not because of global warming, even before the Industrial Revolution, that wasn't possible, but it was possible during this little ice age. So now the question we're asking is it possible that the glaciers are retreating simply because we got out of the little ice age? That really is our focus today from the beginning to the end. Any questions about that question that we're asking? So again, the question is, are these glaciers melting and retreating simply because there was a little ice age that was a naturally occurring cold period that lasted 200 or 300 years, and then we got out of it and it's getting warmer and the glaciers are melting? That's a possible explanation. We need to rule that out, right? Questions? Yeah.
How did the temperatures during the little ice age compare to like a normal ice age?
No comparison. The little ice age is just a fraction of a degree. A full ice age in global mean temperature is like 4 degrees. Where we are now, there was a mountain of ice during the last ice age, so that's 20,000 years ago. There was a mountain of ice of about a mile or such, while the little ice age is this small fluctuation in the temperature that did lead to these observable things that are seen in this classic art, but there's really no comparison to an actual ice age that happens every 100,000 years. Nice question. Great. Okay, so we're going to have 4 lines of evidence that the little ice age is not the reason for the retreat of mountain glaciers that we're observing in the last few decades. So one, we'll see that as the glaciers retreat, plants are found under the retreating glaciers, and these plants contain information that helps us constrain when these glaciers grew. That would be one. We'll see what that means. 2, there is a relation, empirical relation, you'll be calculating that yourself, between the the global temperature or the local temperature and the glacier length. And we're going to use that empirical relation to also deduce whether it's possible that the glaciers have retreated simply because of the end of the little ice age. We're going to look at ice cores. So you remember what ice cores hopefully are. These are cylinders of ice that are drilled in ice in glacier mountains, and these contain a couple of different hints about this issue as well. And finally, just from the understanding of the flow of ice in mountain glaciers, we would be able to again deduce that these mountain glaciers are not retreating because of something that happened 150 years ago, the end of the little ice age. So this is the outline of our plan for today. Let's start from the first one. A very simple evidence that is very widespread and very powerful. Let's start with that. So what you see here is an example of a retreating glacier. You can see that the extent of the glacier in previous years. You can see pictures from 1978 to 2005. And then when this glacier retreats, and you can see the retreat here, when the glacier retreats, here's what we find. We find these plant samples. And when you have organic matter, you can now date it. So you can find that the date of this plant material is 5,000 years. And the idea is that the glacier expanded into that area 5,000 years ago. The plant was covered and basically was preserved in cold temperatures for 5,000 years. And now that we're retreating, we can date it and find out that it grew 5,000 years ago. And that rules out the possibility that the glacier only advanced, say, 300 years ago, because then that plant wouldn't be 5,000 years old. And also, as you'll see in a second, sometimes they find these plants and they're able to regrow them, because it's always possible that the plant grew 5,000 years ago, the glacier retreated and advanced a few times. But then if you take this plant material that is 5,000 years old and you manage to grow it, it means that it wasn't repeatedly exposed to withdrawals and advances of the glaciers, because otherwise it wouldn't be able to be regrown now. So we know that this plant was exposed last time, this area was exposed last time only 5,000 years ago, and therefore we know that this glacier is not just retreating after a small advance that happened over the last couple of hundreds of years. Make sense? Is the logic clear? Questions? Okay. And people know about carbon-14 dating? Okay, okay. Great. Here's another one. In this case, it's even more powerful. So in this area in the Arctic, Canada, you see they find samples from retreating glaciers. They go and date the recovered plant material, and the ages are 40,000 years. So the retreat that is seen in Arctic Canada, not only is it not a retreat after an advance that happened 300 years ago or 200 years ago, it actually is a retreat for a glacier advance that happened 40,000 years ago. So definitely, this retreat of glaciers that we're seeing now is very unusual for the last tens of thousands of years. So nothing to do with the Little Ice Age again. Here's another one. So you see the glacier area, again in the high Arctic, northwest Greenland. And these are the plant materials that you see. And these are the plants that actually grow once the glacier retreats. So the fact that they grow, as I mentioned before, means that these plants were indeed covered by ice and preserved for, thousands of years. So the conclusion from this first line of evidence is pretty straightforward, that the dates of this exposed plant material indicates that these glaciers are retreating from an advance that happened thousands of years ago, as opposed to 200 years ago from the Little Ice Age. So nothing having to do with the Little Ice Age. It's possible that the beginning of the retreat at 1850 is indeed the response to exiting from the Little Ice Age, but there's no question that the more intense retreat that we're seeing in the last few decades, that has been dated here to be thousands of years old, is not related to the Little Ice Age. Okay, questions about this first line of evidence? Okay. Okay, our second line of evidence is that we'll see that there's an empirical relation which actually makes sense from a physical point of view between the temperature and the extent of the glacier. So let me first introduce some basic concepts, and then we'll get into this relation, and then we'll understand how that relation between the temperature and the glacier extent can help us understand why the Little Ice Age has nothing to do with what's happening in the last few decades. So some basic concepts, first of all. So here's a mountain glacier that's extending to one side of the mountain, and there's generally an area of accumulation here up to some line. So in this area, if you go over the entire year, there's accumulation in winter and possibly some melting in summer, but there's net accumulation over that area. While below that line, that's called the ablation area, is where you have less accumulation than melting. Can someone tell me why is it that the ice doesn't continue growing here and why doesn't it shrink here to zero?
Because it flows.
It simply flows, right? So there's a flow from here to here, and that balances the excess accumulation here and the excess ablation here. So this is called the equilibrium line. And you have the accumulation and the ablation zones above and below this area. Okay, that's one. The next concept we want to cover is surface mass balance. So SMB is simply at each location along the glacier, there's going to be a net accumulation or net ablation, net melting, and that's referred to, so either net accumulation at the surface or net melting at the surface, and that's referred to as the surface mass balance. Clearly ice mass balance, okay? So that is the forcing for the glacier. And it's going to be positive in the upper part and negative in the lower part. And then there's the concept of positive degree days. So PDD. What that is, if I look at the record of temperature, and this is 0 Celsius, say, and the temperature here looks like this, and suppose this is 2 degree, 1 degree, 2 degree, 1 degree. Basically, for each day, so these are different days, I'm simply counting how many degrees above zero there are. So for example, if my temperature record, the daily temperature record is equal to -2 degrees, 0 degrees, 3 degrees, 1 degree, 5 degrees in different days, the positive degree days is going to be nothing here, and then 3 plus 1 plus 5 is the PDD. Okay? So that's going to be equal to 9, so the PDD is 9. There's empirical evidence that the melting of the glacier is proportional to the BDD. That's why we're interested. And of course, it has to do with temperature. And our entire interest right now is on the relation between temperature and glacier extent, which is why I'm telling you. So let's write the mathematical expression for this. So this is equal to sum over days. And a day is measured by the index I of Ti, the temperature at day I, minus T melt, which I assumed there was 0 degrees Celsius, times the Heaviside function of Ti minus T melt. So this term makes sure that this is 0 if T melt is higher than Ti. Let me indicate that. So this is 0 if Ti is less than T melt, and 1 otherwise. Okay? And then once we apply this factor of zeros, this counts the degrees above melting, which is what I did in that example over there. Okay, so what I'm telling you is that there's an empirical evidence that the amount of melting depends on this PDD, so there's clearly a relation between melting and the temperature, and therefore it's not surprising that there's going to be a relation between the length of the glacier, which depends on melting, and the temperature. Great. So now that we know that there's a relationship between temperature and melting, you won't be surprised to hear the following thing. So relating glacier length to temperature. So suppose the glacier length is given by L, say in kilometers, and the temperature is given by T. And this would be the temperature around a specific glacier. And suppose that at some time t0, L is equal to L bar, and T, the temperature is equal to T bar. So this could be, say, 1960, for example. Okay? I'm going to define the anomaly length and the anomaly temperature as the deviation from that. So L prime is defined to be L minus L bar. So this is the deviation of the length from 1960. And T prime is going to be equal to T minus T bar, which is the deviation of the temperature from the temperature in 1960s. So T prime and L prime are both 0 in 1960, if that's what we chose for our T0. And there's going to be the following relation that L prime is proportional to T prime. So I'm going to write it as an equal to. Do we expect L prime to grow with T prime? Decrease with T prime? Decrease. So there's going to be a minus and a C here. And C is the climate sensitivity of the glacier. What are the units of C? So the units of C, something like kilometers per degree Celsius. Okay? So it's a simple linear relationship that we're assuming, but empirically it seems to work well. Okay, great. Now here's the problem. This is an equilibrium relation. That is, if we set the temperature to T prime, the temperature anomaly to T prime, and we allow the glacier to adjust, this would be the length of the glacier that has adjusted to this temperature anomaly. Okay? But we need to give it time to adjust because it takes time. Say if the temperature increased, the glacier needs to retreat. That takes some time. And then once it's adjusted, whatever amount of time this takes, decades typically, as you'll see, then this would be the relation between the two. So this is the equilibrium relation between temperature anomaly and length anomaly. Any questions about the equilibrium relation? And this number is interesting because if it's large or small, this determines how sensitive the glacier is to temperature. Okay? And different glaciers may have different sensitivities. The sensitivity might depend on the topography, like if the slope is high or low, the amount of accumulation, the cloud cover, things like that, the latitude. So that glacier sensitivity C is a variable that needs to be calculated for each glacier separately. So again, any questions about any of that? Okay. Great. Now the thing is that when anthropogenic global warming happens, temperature is moving quickly, so T prime is changing rapidly, and therefore the glaciers don't have enough time to adjust, and this relation is not satisfied. So let's make a comment of that. So if the temperature changes rapidly, L prime does not have time to adjust, and then L prime is not equal to minus C T prime, we need a new equation. To relate it to. That is the problem we're facing right now. Okay? What would be that equation? Turns out we could write something that would be really trivial. Allow me to write it and then I'll explain. So we have dL prime dt is equal to minus 1 over tau L prime of t plus C T prime of t. Okay, parenthesis here. Okay, let's see why this makes sense. First of all, suppose this is an equilibrium. In equilibrium, dl dt is equal to what? 0. Equilibrium means that things don't change in time, so therefore the rate of change of the length anomaly is 0. And if that is 0, then we get that L prime is equal to minus Ct prime, which is exactly the equilibrium location. So this reduces to the equilibrium relation if we have an equilibrium. Okay. Why does this make sense for a non-equilibrium situation? That's also not difficult to understand. So you could see that L prime reacts as long as L prime is not equal to minus Ct prime. So if they're different, the left-hand side would not be 0 and L prime would be changing. So as long as the glacier is not at its equilibrium length, which is this, it will change until it fits the equilibrium, until it reaches the equilibrium. And if T prime keeps changing, it may never reach that equilibrium, but it's continuously striving to get to that equilibrium. And tau is the time scale over which it's trying to adjust. So if tau is very small, then this term is very large, the rate of change is large, and the glacier quickly will arrive to its equilibrium. While if tau is large, say hundreds of years, it would take a long time for the glacier to adjust to its equilibrium position. Any questions about this? Okay. So what can we do with this? Well, if we have a record of L of t, so given an observation of L of t, let's call it L prime of t, we can calculate dl prime dt, and then we know this. Let's write it here. So we know dl prime dt is known, minus 1 over tau. Suppose we know the time scale for this glacier. L prime of t is known, plus c. Let's assume that we know c, times t prime of t. So we can actually calculate this. So if you want, we can reconstruct the temperature from the glacier length record. And if that temperature that we reconstruct that way fits the actual observed temperature there, then we know that this relation is correct. Okay? So what we're doing here is we have a length record. From the record, we can take the derivative of that and calculate the LDT. So we know that. We know the time scale. We know the record of length. We know the glacier sensitivity for that glacier. We're assuming that we know all of these. And then we can calculate the temperature from that, and then we can compare it to the observed temperature for that glacier. And if they're the same, then we conclude that indeed this equation describes the adjustment of that glacier. Okay? So we can actually write the solution for the temperature as function of these variables. So that would be T prime of T is equal to minus 1 over C L prime of T plus tau dl prime dt. This is the temperature as function of these other things that we're assuming are known. So let's see, just a review of what we said so far on the board. So this is the glacier. Remember the zone of accumulation, the upper part, the zone of ablation, and the equilibrium line here. And so we discussed these three different areas and the flow, ice flow that connects the accumulation and the ablation zones. The surface mass balance is the rate of snow accumulation minus the surface melting. And the positive degree days is simply summing the temperatures above 0, above the melting temperature, using this expression. Okay, and then we wrote down this equilibrium relation between L prime and T prime, the anomaly length and the anomaly temperature. This assumes that the temperature doesn't change and the glacier has adjusted to that temperature, and at that point, this is the relation between the length and the temperature anomalies. Okay? And then we said that if the temperature changes too quickly, the length may not be in equilibrium, and then this equation describes the rate of change of the the glacier length as function of this changing anomaly temperature. This is the situation in the last few decades. And then we wrote down the temperature solution. And finally, to answer Sarah's question, suppose we were in the 1960s, L prime was 0, T prime was 0, and then we abruptly changed the temperature to be something higher. There was an abrupt warming of 3 degrees. So T prime is now 3 degrees, and it remains constant. So the temperature, T prime, this is some T0, was at 0. This is T prime, and this is the time here. There was some T0, the temperature anomaly was 0, and then it jumped, and then it remains at T0 prime. In that case, this equation becomes a simple equation because that's not a function of T anymore, and this can be solved, and this is the solution. So what does this solution show us? You could check later that that solution indeed holds, so you can plug it back into the equation and see that it solves that equation. I think we're asking you to do that, but let's see what it does. First of all, as T goes to infinity, this term is a decay term, so all of that decays, and we're left with L prime will go to minus C T prime, so that's again the equilibrium relation between the two, so that makes sense. But on the way to that, you can see an exponential decay of the length toward the equilibrium extent of the glacier. And if we had then a plus sign in that place, Sarah, then this would not be decaying toward, and that's why the minus sign is there. That was a good question. Okay. So, okay, well, I don't know if you got to this point, but I think unless you want to continue with the previous one, but I think it might be helpful to jump to this workshop, even if you didn't find the other one, so that you can sort of try to understand what this whole relationship between the glacier anomaly length and the anomaly temperature is. That would help you sort of absorb that material. So let's take a pause and see, are there any questions about what we've done here? Or is everyone clear? What did people get for the value of tau that gave you a best fit?
15.
15, 20. What does that mean? So now you drew the exponential decay. So if I change the temperature in 1850, when would the glacier respond? 15, 20 years later, so definitely not 150 years later. So we understand what this is all about, right? That was the point of this entire exercise. Okay. And the other thing so what did we learn? One, we learned that the response time that you calculated using this best fit is very short, so it's not likely that the change of the temperature due to the recovery from the little ice age is leading to the retreat of glaciers today, 170 years later. That's one. Two, you can see that the reconstructed temperature, which is the red line, is pretty close in character, right, to the observed temperature. So what do we see in the observed temperature? We see an increase, and then a plateau, and then an increase again. And this is the one reconstructed from the glacier length. So an increase, a plateau, and an increase again. So that indicates that the glaciers indeed respond to the temperature based on that equation that we wrote. Also, it's interesting that if you just take the equilibrium temperature reconstructed from the glacier length, you don't get that pose. It looks completely different. And what is the difference between the two? The difference is that in the dashed line, we assume that the glacier is always in equilibrium with the current temperature, and that tells us that this is completely wrong because that dashed line doesn't look like the observed blue temperature here. So we've learned that the response time is 15, 20 years in this case, in this analysis, and that the equilibrium glacier length isn't relevant. What's relevant is the other one because the temperature changes too rapidly for the glacier to always be in equilibrium with the observed temperature. Okay, any questions about that? Okay, so given that, let's see what else. Yeah, so let's get a bit further. So these are the temperatures reconstructed in an actual scientific paper where we took this idea from. Orleman is a well-known glaciologist, and he took these glacier length records. For each of them, C and tau were known from glaciological work. So these was 160-something glaciers, and people knew what C and tau are for these, and you also know what the temperature for each of them is. And then these are the, as you know now, binned temperature and the number of records and so on, the binned glacier length and the number of observations and so on. And this is the reconstructed temperature. And you can see again the increase, plateau, and increase again. So that's what you did yourself, but this is the original scientific work that you were following. Okay, what's the conclusion from this part of what we did today? So this is the second line of evidence. The idea is this: the close relation between the glacier extent and the temperature indicates that glaciers are affected by the recent warming over the last few decades that has nothing to do with the exit from the little ice age 150 years ago. And also the response time scale that you calculated of a few decades guarantees that what we're seeing now in terms of glacier response isn't related to the temperature changes 150 years ago. So that was our next line of evidence. Okay, and this is the second thing that we see here. So this is again delta 018. This is an average over many ice cores in Peru. This one is also in Peru. And so you see, again, a bin average. So this is a decadal average. A bin in this case means you take the temperature every 10 years and you average all the temperatures from all the records from different mountain glaciers in a given decade, and you get this record like this. And what you see is the temperature being constant since 250 all the way to this period. Now you see a decline. This is presumably the little ice age. And then you see a recovery. And then you see the temperature increasing beyond the recovery here. So this record goes to 2000. If you go to 2020, you'll probably see it increasing further. But this is an evidence of the presence of the little ice age that we've heard about from European sources, possibly indicating that also the signal in South America. Okay, so the conclusions from the isotopes. So that was our third line of evidence. We have that the isotopes can be used as a proxy of the temperature. So this is the decrease and increase we see as we get into and out of the little ice age. So that just reaffirms what we knew about the little ice age. And also, this shows that there was an unusual warming in the last few decades right here, possibly. And the other thing is that the melt events seen by the erasing of the seasonal cycle indicate unusual melt events over the last few years. So this is the third line of evidence that what's happening now is unusual and is not a result of the exit from the little ice age. Any questions about the third line of evidence? Okay, moving to the fourth one. So the fourth line of evidence has to do with the flow of ice, right? Let's look at that. So first, some video of flowing ice. That's really beautiful, I think. You can see the ice flowing, right? It's not a solid, it's a fluid. Isn't that impressive? Here's another one. So you see this area right here is a mix of glaciers and sea ice and so on, and the area to the right of that is the actual glacier flow that is flowing, and then it's breaking into the ocean, and then you have this melange of glaciers and sea ice and so on. But you could see the front of the ice retreating, this stuff. So you want to Google this extreme ice survey and look at some videos that they have, because it's pretty impressive. These are lapse photos of glacier flow in different places that are really impressive. Okay, so now we know that ice flows. What is the consequence of that, and what does this have to do with the little ice age, our problem today, right? So glacier dynamics. So what do we see here? Suppose we had the glacier that looked like this blue line. This was a mountain glacier covering the entire blue part. And this is the surface mass balance. So we talked about surface mass balance is the difference between accumulation and melting as function of height. So initially it was this blue line right here. So this means that above 5 kilometers, the ice is accumulating, and below 5 kilometers, it's melting. Look, this is 5 kilometers. There's plenty of ice under that line because this ice right here flew from the upper part. We saw the videos of the ice flowing. That's how this ice got here to be all the way from 4 kilometers to 5 kilometers. It's not fed by accumulation. It's fed by ice flow. Okay? And then suppose there was global warming. So now we have more PDD, more positive degree days, more melting. This means that the mass balance changes. So now the new mass balance is the dashed red line, and that is positive only above 5.5 kilometers. So the ice sheet responds. Not the ice sheet, but the glacier, the mountain glacier responds. And the blue area here denotes the area of the ice sheet, of the mountain glacier, after this change, after this the equilibration to the new ice mass balance, surface mass balance. So you can see that now the glacier is being fed only above 5.5 kilometer and extends only to about 4.5 kilometer. So everything went up. You know, the lowest extent of the glacier went up from here to here. The zero line, the equilibrium line, moved from here to here. And the ice flow now feeds everything below the red line instead of being able to feed only instead of needing to feed only the part that is below the dashed blue line. Any questions about this scenario? This, by the way, is calculated by a model of ice flow. It's a simple model. We won't get into the equations, but just like people have mathematical models of the flow in the ocean and the atmosphere, they have mathematical models for the flow of ice, and this is the result of such a model. Okay. Now, we're interested in the adjustment timescale, and this is just the equilibrium before and after. So let's look at the following picture. Let's start with this. So this is the glacial extent in that simulation. Remember what happened is at t equals 0, the surface mass balance changed. The equilibrium line moved up by 500 meters. And this is what the glacial length looks like. So for a while, it doesn't respond. The glacial length does not respond, even though we now have more melting and the equilibrium line is higher. The glacial length initially does not respond. Then suddenly, the glacial length responds. And by 40 years, it's done responding, and it's at the new location. So the question is, why is it that the glacial length did not respond? Is the mystery clear? So let me explain this again. At t equals 0, we moved from one mass balance to the other. Let me remind you. The surface mass balance was the blue line. So we had accumulation about 5 kilometers and melting below 5 kilometers. Now it changed. Now we have accumulation above 5.5 kilometers and melting below 5.5 kilometers. So suppose this change happened abruptly. Now we want to see what is the response of the glacier length from that model that I just mentioned. And here's what we find. So initially, the glacier length doesn't respond, and then suddenly it drops rapidly. By 40 years after the change, it's completely equilibrated to the new length. So we saw the length changes. Now let's look at the thickness. So the different lines here show the thickness in different times. So the initial thickness was the thick blue line. The final thickness was this red line. So you see the initial one extended about 6.5 kilometers. The final one is 5 and something kilometer. And the lines in between indicates how the thickness changes. So first of all, you see that initially, these thin lines, the glacier becomes thinner in this area. You know, this is the top of the mountain. This is the part that's retreating. Initially, the thickness changes, but the length does not change because this line right here ends at the same place. So the ice becomes thinner first. So as we decrease the surface mass balance because of the increase in PDD, positive degree days, the glacier gets thinner, and then it starts retreating. So that's exactly what happens here. During this initial period, the glacier was getting thinner, but the extent was not becoming smaller. So now you have glacier becoming thinner, and then eventually it starts retreating. You see the end line here retreating gradually, and then until it gets to this point. So this delayed response is simply the time in which the thickness of the glacier changes while it didn't start changing in extent. The length was not changing. So the whole thing is pretty consistent, and the bottom line is 40 years is a sensible time for a glacier length to respond, and therefore, if the little ice age happened ended at 1850, there's no way that many years later we're still seeing a response to that. So I mean, any way you look at it, 4 very different lines of evidence, from a mathematical model all the way to plant material that we expose under the ice, all tell you that this has nothing to do with the little ice age, because you do go to some of these places and you run into a skeptic and they say, yes, but they told me that this glacier retreated in 1900. Well, 1900 it retreated in response to the little ice age ending, but the retreat that we see today, which is much faster and more dramatic, is because of the current warming. It's kind of nice to say there's not much uncertainty here, admittedly. It's pretty straightforward, right? We don't have that in every subject that we cover.
Wait, this is kind of related to one of the questions, like the guiding questions, but does this mean that we can detect climate change or that we can attribute this to climate change?
Nice. Okay. I would say all of these lines of evidence mean that we can attribute the changes over the last 40 years to anthropogenic climate change. Okay? The retreat that happened in the 19th century is possibly due to the exit from the little ice age. But what we're saying is that the retreat we observe over the last 40 years, which was very dramatic, as we saw in the before and after pictures, all of that retreat is due to anthropogenic global warming and nothing else. Okay. So the conclusion from this one is that from this mathematical flow model of the ice and from the observations of how rapidly ice flows that we saw in these time-lapse videos, we know that the response time is fast, so maybe decades, and again shows that the mountain glaciers today can't be responding to something that happened around 1850. Nice. Okay, summary. So what do we see? We see a dramatic retreat of mountain glaciers worldwide. There are very few exceptions, locations where mountain glaciers expand rather than retreat. People have been looking at these isolated locations, and typically there's some explanation. If you come to me, I'm happy to tell you about some examples in the Himalayas and so on, where glaciers are expanding, a few places in the Himalayas, and there's an explanation for this. But overall, there's a dramatic retreat of mountain glaciers everywhere in the world, from Africa to Alaska and Greenland. Okay, so there's plenty of evidence that this is not a natural response to the naturally occurring little ice age, and we surveyed several lines of evidence. So first of all, these exposed plants, we date them and we conclude that the glaciers advanced to these locations from which they're retreating today, possibly thousands of years ago. So definitely not an advance that happened at the beginning of the little ice age. Okay, next. There's the relation between temperature and glacier length that you guys plotted. So that shows that the close correspondence between glacier length and temperature indicates that the changes in glacier length we're observing over the last 4 decades are related to the temperature changes over these final decades, recent decades. So that's another point. I didn't say it in these words, but the fact that we're seeing accelerated retreat in the last few decades is inconsistent with the response of ice sheets to an old change, because if this was an old change, we would now be in the phase of slow adjustment to that old change, and we see acceleration of the change now. The adjustment time we calculate is short, so it's inconsistent with such a late response to the little ice age. The isotopic records, we learned 2 things. One, we saw the delta O18 as a proxy for temperature. We saw there the little ice age and the recent warming. And 2, we saw the melt events that occurred recently and didn't occur for many, many years before. So I think all of these lines together bring us to the bottom line that these mountain glaciers are retreating because of anthropogenic global warming, because of the increase in greenhouse forcing. All right, any final questions? The end. See you next time.
Thank you.